Did you ever stare at a stubborn coffee stain on your favorite white t-shirt and wonder, how on earth does bleach actually make that disappear? It feels like magic, right?
Yeah. Yeah.
But the truth is, it's not magic at all. It's the intricate chemistry of how organic compounds interact with light.
That's right. And today we're taking a deep dive into the fascinating world of conjugated pi systems and the truly special reactions they undergo, known as paracyclic reactions. Our guide for this journey is Chapter 16 of David Klein's Organic Chemistry, which, lays out the unique structure, properties, and remarkable reactivity of these molecules.
So get ready because we're going to unpack some truly core concepts, explore intricate mechanisms, uncover practical applications, and hopefully make what might seem like complex organic chemistry crystal clear and utterly engaging for you. Let's dig in. All right, let's start with the foundation. When chemists talk about dienes, what's the fundamental characteristic we're looking at?
Okay, so dienes are simply organic compounds with two carbon-carbon double bonds. Pretty straightforward.
Just two double bonds anywhere.
Well, that's the thing. The real story, and what defines their unique behavior, is the arrangement of those double bonds.
So not all double bonds are created equal, even if there are two of them.
Precisely. We classify them based on how close those pi bonds are. You have cumulated dienes, also called allenes, where the pi bonds are directly adjacent, sharing a central carbon. Kind of bunched up.
Okay.
Then there are isolated dienes, where the pi bonds are separated by two or more single bonds. They essentially behave independently, like two separate alkenes.
Right, too far apart to really interact.
Exactly. But the true stars of our deep dive are conjugated dienes. Here, the pi bonds are separated by exactly one sigma bond.
Just one single bond in between.
Yes. And this seemingly small detail allows for a continuous system of overlapping orbitals. Think of it like a molecular highway, where electrons can roam freely across several atoms, rather than being confined to just two.
A molecular highway. I like that.
Yeah, and this electron highway is what gives them their special properties and reactivity. And it's not just carbon-carbon double bonds. A carbon-carbon pi bond can also be conjugated with other types of pi bonds, like those in carbonyl groups, forming, for instance, a conjugated enone.
So it's that continuous overlap, that conjugated system that creates this electron highway. But what does that continuous system do? How does it make them special?
Excellent question. Well, first, let's briefly touch on how we prepare them. Conjugated dienes can often be formed through elimination reactions from, say, allylic halides or dolides. You often need sterically hindered bases like potassium tert butoxide to favor elimination over substitution.
Right, got to prevent those side reactions.
Exactly. Now, onto their unique properties. One fascinating aspect is their bond lengths.
Okay.
The single bond connecting the two double bonds in a conjugated dubond, like in 1,4,8-litidianin, is surprisingly shorter, about 148 picometers, compared to a typical carbon single bond like an ethane, which is around 153 picometers.
Shorter. Why is that?
It's not just a minor detail, it's a direct result of hybridization. That central bond forms from the overlap of two sp2 hybridized orbitals, which have more Nis character than sp3 orbitals.
More ease character means the electrons are held closer to the nucleus.
You got it. Pulling electron density closer and making the bond inherently shorter?
That makes sense. It's like the electrons are pulled in tighter. And what about stability? Does this electron delocalization make them more stable?
Absolutely. Conjugated double bonds are significantly more stable than isolated ones. We see this clearly in their heats of hydrogenation.
How so?
Well, if you hydrogenate 1,4,3-butane, it liberates less heat, about 239 kilojoules per mole, than you'd expect if you just added up the heat from hydrogenating 2 moles of 1-butene, which would be about 254.
So there's like missing energy.
Yeah, about 15 kilojoules per mole less heat released. That difference represents the stabilization energy gained from conjugation. That stability comes directly from the electron delocalization across that entire conjugated system.
So they're more stable because the electrons are spread out. Neat.
Oh.
And these molecules aren't rigid, are they? Do they adopt different shapes or conformers?
They do. In 1,5-U butadiene, for instance, there's free rotation around that central C2C3 single bond. This leads to two main conformers.
Okay.
There's the cis, where the double bonds are sort of pointing in the same direction relative to the single bond dihedral angle 0. And then there's the S-trans, where they're pointing opposite ways, dihedral angle 180 degrees.
Like cis and trans, but around a single bond. S-cis and SNANs.
Exactly. The S refers to the sigma bond, and the S-trans conformer is significantly more stable, about 98% favored at room temperature, largely due to fewer steric clashes between the hydrogens.
Makes sense. Less bumping into each other.
Right, and if you try to rotate that central bond by 90 degrees, you actually disrupt the peak orbital overlap, you break the conjugation. The double bonds effectively behave like isolated ones, and that rotation requires energy, about 15 kilojoule, that stabilization energy we just talked about.
Okay, so we've established that these conjugated systems have special structures and enhanced stability. But to truly understand the fundamental why behind all of this, we need to bring in molecular orbital theory, right?
Exactly. Molecular orbital theory, or MO theory, provides that fundamental explanation. Remember, MOs describe electrons associated with the entire molecule, not just individual atoms or bonds.
Right, not just localized bonds.
Think of a simple pi bond, like an ethylene. You have the two atomic p orbitals combining to form two molecular orbitals. A lower energy bonding MO, where the two pi electrons reside, and a higher energy anti-bonding MO, which is empty in the ground state and has a node between the nuclei.
Okay, bonding and anti-bonding.
Now, for 1-3-butadiene, it's four overlapping p orbitals combined to form four molecular orbitals. There will be two bonding MOs and two anti-bonding MOs.
4 atomic orbitals in, 4 molecular orbitals out. Makes sense.
And the crucial insight here is that the 4 pi electrons of butadiene occupy the two lowest energy bonding MOs, SUT1 and S1. Now, if you look at the lowest energy MO at 1, it actually shows electron density distributed across all 4 carbons, including significant density between the central C2-C3 bond.
Ah, so that explains the shorter bond. MO theory shows it has some double bond character.
Precisely. This directly explains why that single bond is shorter than expected and contributes to the overall stability of conjugated dienes through this electron delocalization.
So MO theory literally reveals the hidden double bond character in that single bond. And this leads us to what are called frontier orbitals, right? The HOMO and LUMO.
Yes, the HOMO and LUMO. These are absolutely critical for understanding reactivity. The HOMO is the highest occupied molecular orbital. It contains the highest energy pi electrons, the ones most readily available to participate in reactions, like acting as a nucleophile.
The most accessible electrons.
And the LEMO is the lowest unoccupied molecular orbital. It's the lowest energy orbital that's empty or only partially filled, ready to accept electrons, like from an electrophile. Frontier orbital theory, developed by Kenichi Fukui Nobel Prize work, by the way, tells us that most reactions happen via interactions between the HOMO of one molecule and the LEMO of another.
Okay, so knowing the HOMO and LUMO is key to predicting reactions.
Absolutely. And it's these frontier orbitals that allow these molecules to interact with light, leading to some truly remarkable phenomena.
How does that work?
Well, conjugated pi systems can absorb light, specifically UV or visible light. When a pi electron in the HOMO absorbs a photon with the right amount of energy matching the energy gap between the HOMO and LEMO, it gets excited and jumps up to the LUMO.
So it absorbs the light energy to make that jump.
Exactly. This is called a pi to pi star transition. This absorption changes the identity of the frontier orbitals. What was the LEMO is now occupied, becoming the new HOMO of the excited state. And this photochemical excitation is crucial for certain light-induced reactions.
Okay, that makes sense. It changes the electron configuration, changes how it might react.
Precisely.
So now that we understand the structure and fundamental nature of these conjugated systems, let's talk about what they do. Electrophilic addition, a familiar reaction, gets a pretty interesting twist when applied to dienes.
It certainly does. We've seen electrophilic addition to simple alkenes before, like adding HBr. But with conjugated dienes like 1,3-butadiene reacting with HBr, we typically observe two major products, a 12,2 adduct and a 1,4 adduct.
Two products. How does that happen? What dictates which one forms?
Good question. It still follows a two-step mechanism. First, one of the pi bonds of the diene acts as a nucleophile and gets protonated by the HBr. This forms a resonance-stabilized allylic carbocation. That intermediate is key.
Allylic carbocation. So the positive charge is spread over 2 carbons through resonance.
Exactly. The charge is delocalized between C2 and C4 in the case of 1,3-butadiene protonating at C1. In the second step, the nucleophile, the bromide ion, can attack at either of those two electrophilic positions, either C2 or C4. Attack at C2 gives the 1,2 adduct, and attack at C4 gives the 1,4 adduct.
Ah, so the resonance structure of the intermediate directly leads to the two different products. Makes sense. I imagine other electrophiles like Br2 would behave similarly.
They do. Adding Br2 also yields both 1-2 and 1-4 adducts. And this is where the critical concept of kinetic versus thermodynamic control comes into play. It's a really important idea in organic chemistry.
Kinetic versus thermodynamic. Okay, I got it down.
So if you run the reaction at low temperatures, say 0 degrees Celsius or even lower, the reaction is under kinetic control. This means it favors the product that forms fastest, the one with the lower activation energy barrier.
The quickest product wins.
Exactly. For HBr addition to 1,4,3-butadiene, the 1/4 adduct usually predominates at low temperature, maybe like 70–80%. This is often attributed to a proximity effect. After the proton adds to C1, the bromide ion is simply closer to C2 than it is to C4, so attack there is faster.
So at low temperatures, it's like taking the quickest route, even if it's not the most stable final destination.
That's a great analogy. Now, if you run the same reaction at a higher temperature, say 40 degrees Celsius, things change. It's now under thermodynamic control. Meaning there's enough energy for the reactions to be reversible. The products can potentially revert back to the allylic carbocation intermediate, an equilibrium is established, and the reaction favors the most stable product overall, regardless of how fast it forms.
The most stable product wins in the long run when things get equilibrate.
Precisely. In the HBr addition case, the 1/4 adduct is typically the thermodynamic product because it often has a more substituted double bond, which is generally more stable according to Zaitsev's rule. So at 40 degrees C, you might see maybe 80–85% of the 1/4 adduct.
So low temp favors speed, kinetic 1/4 adduct. High temp favors stability, thermodynamic 1/4 adduct.
Got it.
That scenic route principle must have massive real-world implications, right?
It absolutely does. This very principle underpins how we control the structure and therefore the properties of polymers made from dimensions. Think about natural and synthetic rubbers.
Like tires.
Exactly. Natural rubber is polyisoprene, made from the monomer isoprene, which is a substituted butadiene. Synthetics like neoprene from chloroprene and SBR, styrene butadiene rubber, are crucial materials. These polymerizations often proceed via 1/4 addition to create the long polymer chains with specific properties needed for things like elasticity and durability in tires. Controlling the conditions controls the structure.
That's amazing. From tire rubber to predicting reaction outcomes with temperature. Now let's move on to a whole new intriguing category of reactions that operate under unique principles.
Pericyclic reactions.
Yes, pericyclic reactions. They are truly a special class in organic chemistry because they don't involve the usual ionic or radical intermediates we often see. No intermediates. How do they happen then?
They proceed via a concerted process. This means all the bond breaking and bond making happens simultaneously in a single step without any detectable intermediates.
Wow, like a perfectly synchronized chemical dance.
That's a good way to put it. They involve a ring of electrons moving in a closed loop through a highly organized cyclic transition state. A key characteristic is that their rates and yields are generally unaffected by solvent polarity.
Why is that?
It suggests their transition states bear very little partial charge, unlike, say, SN1 or SN2 reactions. So changing the solvent doesn't dramatically speed them up or slow them down. And there are three major types of pericyclic reactions, categorized by the changes in sigma and pi bonds.
Okay, what are they?
First, you have cycloaddition reactions, where two separate molecules combine to form a ring. In the process, two pi bonds are converted into two new sigma bonds.
Two molecules become one ring.
Then you have electrocyclic reactions. Here, a single molecule containing a conjugated pi system forms a ring by joining its ends. One pi bond is converted into a sigma bond, and the other pi bonds shift position.
One molecule closes up into a ring.
And finally, there are sigmatropic rearrangements. In these, a sigma bond breaks, a new sigma bond forms, and the pi bonds shift their locations within the molecule. The total number of sigma and pi bonds usually stays the same. It's more like a reorganization.
Okay, cycloaddition, electrocyclic, sigmatropic. Sounds like a beautifully choreographed dance of electrons. Let's focus on perhaps the most famous of these, the Diels-Alder reaction, which even earned a Nobel Prize.
The Diels-Alder reaction, discovered by Otto Diels and Kurt Alder back in 1928, Nobel Prize in 1950. It's a true powerhouse in organic synthesis, incredibly useful for making six-membered rings.
What kind of reaction is it?
It's a 4+2 cycloaddition. The numbers refer to the number of pi-electrons involved from each component. A conjugated diane, which provides 4 pi-electrons, reacts with a second component called a diaphile, which provides 2 pi-electrons, usually from a double or triple bond, to form a 6-membered ring, specifically a substituted cyclohexene.
4 plus 2 equals 6 electrons in the transition state.
Exactly. And crucially, 2 new carbon sigma bonds are formed simultaneously in that single concerted step. The transition state is a cyclic arrangement where the old pi bonds are partially breaking and the new sigma bonds are partially forming.
So 2 reactants become one larger ring molecule. What about the thermodynamics? What temperatures do these reactions prefer?
Moderate temperatures, say below 200 degrees Celsius, generally favor product formation in Diels-Alder reactions.
Why is that?
Because the reaction is typically exothermic. You're converting 2 relatively weaker pi bonds into 2 stronger sigma bonds, which releases energy, favorable enthalpy change. However, you are decreasing entropy because 2 molecules are becoming one, and you're forming a ring, which restricts rotation.
So enthalpy drives it forward, entropy works against it.
Right. At moderate temperatures, the favorable enthalpy change usually wins out. But if you crank up the temperature too high, say above 200 or 250 degrees Celsius, the entropy term Ts becomes more significant and starts to dominate. The reaction becomes reversible, and the reverse reaction, called the retro-Diels-Alder, becomes thermodynamically favored. The ring breaks back open into the diene and diaphile.
Ah, so you can sometimes reverse it with enough heat. That's a really clear explanation.
Right.
So temperature is crucial for the reaction's direction. Now, what makes a good dienophile, the 2-atom, 2-electron component?
Good diaphiles typically have electron withdrawing substituents attached to the double or triple bond. Things like carbonyl groups, aldehydes, ketones, esters, cyano groups, or nitro groups.
Why electron withdrawing?
These groups pull electron density away from the dienophile's pi bond, making it more electron poor or electrophilic. This enhances the interaction with the typically electron-rich diene, which acts as the nucleophile. So electron-withdrawing groups make the reaction faster and often give higher yields.
Okay, so an electron-poor dienophile reacts better with an electron-rich diene.
Got it.
Okay.
What about stereochemistry?
The Diels-Alder reaction is highly stereospecific. This means the stereochemistry of the dienophile is directly translated into the product. If you start with a cis dienophile, like maleic anhydride, the substituents end up cis on the newly formed ring. If you start with a trans dienophile, like fumarate, they end up trans. The geometry is preserved.
That's really useful for synthesis. And triple bonds can react too.
Yes, alkynes can also act as dienophiles, leading to cyclohexadenes initially.
Okay. And what about the diene? Does it have any special requirements?
Yes, the diene has a critical conformational requirement. It must be able to adopt a cis conformation for the reaction to occur.
The cis, where the double bonds are on the same side of the single bond? Why? Because in the transition state, the 2 ends of the diene, C1 and C4, need to be close enough together to simultaneously bond with the 2 atoms of the dienophile. If the diene is locked in an S-trans conformation, like maybe due to bulky groups or being part of a ring system that forces it trans, the ends are too far apart and the reaction simply won't happen.
So it needs to be able to twist into that cis shape.
Exactly. This is why cyclopentadiene is a prime example of a highly reactive diene. It's permanently locked in an S-cis conformation by its 5-membered ring structure. It's so reactive it even undergoes a Diels-Alder reaction with itself at room temperature to form a dimer.
Wow, okay. And when dienes like cyclopentadiene react with certain dienophiles, they form those interesting bridged bicyclic compounds.
Yeah.
You mentioned there's a strong preference for the endo product. What's that about?
Correct. When a cyclic diene, like cyclopentadiene, reacts, the dienophile can approach from 2 faces relative to the developing bridge. The substituents on the dienophile can either point towards the larger bridge, the exo position, or away from the larger bridge, tucked underneath it, the endo position. The reaction strongly prefers the endocycloduct, even though it's often sterically more hindered.
Why favor the more crowded product? That seems counterintuitive.
It does. The reason is believed to be a favorable secondary orbital interaction in the transition state. The electron withdrawing groups in the dienophile can have a stabilizing overlap with the developing pi system within the diene part of the transition state. This extra stabilization preferentially lowers the energy of the endo transition state compared to the exo transition state, making the endo product form faster. It's the kinetic product, which also happens to often be the observed product.
Ah, a subtle orbital interaction overriding simple sterics. Cool. And if both the diene and the dienophile are unsymmetrical, can we still predict the major product's regiochemistry?
Yes, the reaction becomes regioselective, meaning one constitutional isomer is formed preferentially. You can often predict the major product by considering the partial charges on the atoms. Draw resonance structures to identify the electron-rich end of the diane and the electron-poor end of the dienophile due to those withdrawing groups. The major product usually arises from aligning the transition state so that the electron-rich part of the diene interacts most strongly with the electron-poor part of the dienophile, aligning the delta minus and delta plus regions.
Maximize those attractive forces in the transition state. Makes sense. This all ties back beautifully to MO theory, doesn't it? How does MO theory explain why Diels-Alder reactions are allowed under thermal conditions while others aren't?
It does perfectly. For a Diels-Alder reaction to occur under thermal conditions, just heat, no light, electron density flows from the HOMO of the diene to the LUMO of the dienophile. The key principle here is the conservation of orbital symmetry, famously articulated by Woodward and Hofmann.
Conservation of orbital symmetry. Well, what does that mean practically?
It means the phases of the interacting atomic orbitals that combine to form the new sigma bonds must align properly. Positive phase must overlap with positive phase, negative with negative for constructive overlap and bond formation to occur efficiently in the transition state. When you look at the HOMO of a typical diamine and the LUMO of a typical dienophile, their symmetries at the ends where the bonds form match perfectly. This allows for bonding overlap on both sides simultaneously, making the Diels-Alder reaction a symmetry-allowed process under thermal conditions.
The orbitals just line up nicely.
Exactly. Now, contrast this with a thermal 2+2 cycloaddition like trying to get two ethylene molecules to react and form cyclobutane just by heating them. If you try to overlap the HOMO of one ethylene with the LUMO of the other, the symmetries don't match. You get bonding overlap on one side, but anti-bonding overlap on the other.
So the phases clash.
Right. This makes the thermal 2+2 cycloaddition symmetry forbidden. The activation energy is prohibitively high because the orbital symmetry isn't conserved in the transition state. However, and this is critical, 2+2 cycloadditions can often occur readily under photochemical excitation, that is, using UV light.
Light changes things again. How?
Remember how absorbing a photon promotes an electron from the HOMO to the LUMO? This creates an electronically excited state. Now, the relevant frontier orbital for reaction is the new HOMO of this excited state, which was the LUMO of the ground state. Crucially, the symmetry of this excited state HOMO is different from the ground state HOMO, and it turns out that the symmetry of the excited state HOMO of one ethylene does match the symmetry of the LUMO of a ground state ethylene.
So shining light changes the orbital symmetry, allowing the 2+2 reaction to happen.
Precisely. Photochemical excitation makes the 2+2 cycloaddition symmetry allowed. The light provides the energy and changes the orbital symmetry rules.
And this ties into a very real and serious practical application, or rather, a hazard.
It does, unfortunately. This very principle explains how UV light from the sun damages our DNA. UV light can cause 2+2 cycloadditions between adjacent thymine bases on the same DNA strand, forming cyclobutane rings that link them together called thymine dimers.
And that messes up the DNA structure.
Big time. It creates kinks and distortions that interfere with DNA replication and transcription. If not repaired properly by our cellular machinery, these lesions can lead to mutations, cell death, and potentially skin cancer. This is precisely why sunscreens, which contain molecules designed to absorb UV light, are so important for protecting our DNA from these harmful photochemical 2+2 cycloadditions. It really makes you think twice about skipping sunscreen, doesn't it?
It absolutely does. Wow. Okay, moving on to another type of paracyclic reaction. Electrocyclic reactions. This is where a single molecule does a kind of internal ring closing or ring opening dance.
Exactly. In an electrocyclic reaction, a conjugated polyene, like butadiene or hexatrine, forms a ring by creating a new sigma bond between its ends. In the process, one pi bond is consumed, and the remaining pi bonds shift their positions. It can also go in reverse. A cyclic compound can ring open to form a conjugated polyene.
Ring closing or ring opening.
And what's truly fascinating here, again governed by the Woodward-Hofmann rules based on conservation of orbital symmetry, is how the reaction conditions, whether it's thermal, just heat, or photochemical UV light, dictate the stereochemical outcome of the reaction.
So you mean the substituents on the ends of the polyene end up cis or trans in the cyclic product, depending on whether you heat it or shine UV light on it? That's wild.
It is. It's one of the most elegant demonstrations of orbital symmetry control. To understand the stereochemistry, we need to look at how the pi orbitals on the terminal carbons of the conjugated system must rotate as the new sigma bond forms. There are two possible ways they can rotate relative to each other. They can rotate in opposite directions, one clockwise, one counterclockwise. This is called disrotatory motion. Think of twisting the ends of a ribbon in opposite ways.
Disrotatory, opposite directions. Got it.
Or they can rotate in the same direction, both clockwise or both counterclockwise. This is called conrotatory motion, like turning two interlocked gears the same way.
Conrotatory, same direction.
Yeah.
Okay, so how does heat versus light pick one?
It depends on the number of pi-electrons involved in the cyclic transition state and the symmetry of the relevant frontier orbital, the HOMO. The Woodward-Hoffman rules, derived from MO theory, give us clear predictions. For thermal reactions, heat, if you have 4n pi-electrons, like 4n pu-to-d-n, the reaction proceeds via conotatory motion to maintain orbital symmetry. If you have 4n plus 2 pi-electrons, like 6 in hexatrine, the reaction proceeds via disrotatory motion.
Okay, 4 electrons thermal, conrotatory, 6 electrons thermal, disrotatory.
Exactly. Now, for photochemical reactions, UV light, the rules reverse, because excitation changes the homosymmetry. So, for photochemical reactions, 4n pi-electrons, like butadiene, proceed via disrotatory motion, 4n plus 2. Pi-electrons, like hexatrine, proceed via conrotatory motion.
Wow, so light literally flips the required rotation and thus the stereochemical outcome. If thermal gives cis, photochemical gives trans, or vice versa, depending on the system. That's incredible control.
It really is a mind-bending chemical switch dictated purely by orbital symmetry and whether you use heat or light. It lets chemists predict and control the precise 3D shape of the product formed.
Incredible how light can completely flip the stereochemical outcome.
Finally, let's quickly look at the third category, sigmatropic rearrangements.
Right, sigmatropic rearrangements. These are intramolecular reactions where a sigma bond appears to migrate across a conjugated pi system. Technically, one sigma bond breaks, the pi bonds shift, and a new sigma bond forms at a different location. The overall number of sigma and pi bonds usually stays the same. It's more like a reorganization or shuffling of bonds. Like musical chairs for bonds.
Yeah, something like that. They are classified using numbers in brackets like 3, 3, or 1, 5, which indicate the positions relative to the original sigma bond where the new sigma bond forms. Two of the most famous examples are the Cope and Claisen rearrangements, both being 3-3 sigmatropic rearrangements.
Okay, what are they?
The Cope rearrangement involves a 1,5-diene rearranging. All 6 atoms involved in the cyclic transition state are carbons. The equilibrium often favors the product where the double bonds end up being more substituted and thus more thermodynamically stable.
And the Claisen.
The Claisen rearrangement is essentially the oxygen analog of the Cope. It involves the rearrangement of an allylic vanillic ether. It also proceeds through a 3N3 cyclic transition state. This reaction is particularly useful because it strongly favors the products due to the formation of a very stable carbon-oxygen double bond, a carbonyl group, in the product. It's also commonly seen with allylic aryl ethers, where the initial rearrangement disrupts aromaticity, but is quickly followed by tautomerization to reform the aromatic ring, resulting in an ortho-allyl phenol.
So these rearrangements allow for some clever ways to shift functional groups around a molecule. Are there any real-world applications for these rearrangements too? Or electrocyclic reactions?
Absolutely. One of the most fascinating and vital examples involves the photoinduced biosynthesis of vitamin D in our own bodies.
Vitamin D from sunlight.
Yeah.
How does that involve pericyclic reactions?
Well, in our spin, a molecule called 7-dehydrocholesterol, a precursor derived from cholesterol, absorbs UV light from the sun. This triggers a photochemical electrocyclic ring opening reaction, specifically a 4n plus 2 electron system opening under light, which is conrotatory to form pre-vitamin D3.
Okay, a light-triggered ring opening.
But that's not the end of the story. Pre-vitamin D3 then undergoes a thermal sigmatropic rearrangement, specifically a 1-Ural-7 hydride shift, which is symmetry allowed under thermal conditions, to form vitamin D3, calciferol, the active form. This same sequence is even used commercially to irradiate precursors to fortify milk with vitamin D.
That's incredible that the very sunlight that can trigger a problematic 2+2 cycloaddition in DNA also helps us make vital nutrients via a different sequence of pericyclic reactions. An electrocyclic, followed by a sigmatropic. Amazing interplay.
It really highlights the elegance and power of these seemingly abstract chemical principles in biology.
Speaking of light and seeing things, how do we actually see these conjugated systems in a lab setting? How do we analyze them?
That's where UV-vis spectroscopy comes in. It's a fundamental technique for studying conjugated systems.
UV-vis. Ultraviolet visible light.
Exactly. This technique studies the interaction between matter and the ultraviolet, roughly 200-400 millimeters, and visible, roughly 400-750 millimeter regions of the electromagnetic spectrum. Conjugated pi systems are perfect for this because, as we discussed, they absorb light in this region to promote those electronic excitations, the pi to pi star transitions from the HOMO to the LUMO.
So we measure how much light they absorb.
Precisely. A UVV spectrophotometer shines a beam of UV or visible light through a sample solution and measures the intensity of light that passes through transmittance, or, more commonly, how much light is absorbance, at different wavelengths. This data is plotted to generate an absorption spectrum, which shows absorbance versus wavelength.
And what's the key information we get from that spectrum?
The most important feature is the wavelength at which the maximum absorption occurs. This is called Valmax, lambda max. It corresponds to the energy gap between the HOMO and LUMO for the most probable electronic transition. We can also quantify the amount of absorption using Beer's law. A equals epsilon.
Beer's law, Ag epsilon. Remind me what those terms are.
Sure, A is the measured absorbance, which is unitless. Epsilon is the molar absorptivity, also called the extinction coefficient, which is a characteristic constant for a given compound at a specific wavelength, indicating how strongly it absorbs light. C is the concentration of the sample, usually in mole, and L is the path length of the light beam through the sample, usually the width of the cuvette, often 1 centimeter.
Okay, absorbance depends on how much stuff is there and how strongly it absorbs. And this nomax value tells us something crucial about the extent of conjugation, right?
Yes, absolutely crucial. There is a direct correlation. Compounds with a greater extent of conjugation, meaning more double bonds linked together in that continuous pi system, will have more molecular orbitals, and critically, the energy gaps between these orbitals, especially the HOMO-LUMO gap, become smaller.
Smaller energy gap.
Means less energy is required to excite an electron. Since lower energy corresponds to longer wavelengths of light, remember E equals P, compounds with more conjugation absorb light at longer wavelengths. So increasing conjugation leads to a longer max, shifting the absorption towards the visible region. Each additional conjugated double bond typically adds about 30-40 millimeters to nu max.
So more conjugation and longer wavelengths absorption. Got it.
We call the part of the molecule responsible for the light absorption the conjugated pi system itself, the chromophore. And any groups attached to the chromophore that modify its Lmax or absorption intensity are called oxochromes, like alkyl groups, hydroxyl groups, etc.
Chromophore and oxochromes. Are there ways to predict Lmax?
There are. Chemists developed empirical rules, most notably the Woodward-Pfizer rules, that allow you to estimate the Lmax for conjugated dienes and enones based on the basic chromophore structure, plus contributions from various oxochromic features like additional conjugated double bonds, alkyl substituents, double bonds that are exocyclic to a ring, or whether the diene is within a single ring, homoangular, or spread across two heteroannular. They work reasonably well for simpler systems, giving you a ballpark prediction.
So we're literally seeing the unseen structure through how it interacts with light. And this brings us right back to our initial puzzle. How does bleach actually make that coffee stain disappear?
Bleaching agents, like sodium hypochlorite, are oxidizing agents. They work by chemically reacting with the colored compounds in the stain. These colored compounds, like tannins in coffee or pigments in grass stains, owe their color to highly extended conjugated pi systems that absorb visible light.
So bleach attacks the conjugation.
Exactly. The bleach reacts with and breaks up that extended conjugation, often by oxidizing double bonds or cleaving the molecule into smaller fragments. These smaller fragments have much less conjugation, or none at all. As a result, their Lmax shifts from the visible region into the ultraviolet region. Since they no longer absorb visible light, they appear colorless to our eyes. The stain hasn't really gone. Its molecules have just been chemically altered so they don't interact with visible light anymore.
Wow. So bleach makes things invisible to us by breaking their chromophores.
Yeah.
That's clutter. And sunscreens work similarly.
Sort of, but protectively. Organic sunscreen molecules are specifically designed conjugated pi systems that have a very high molar absorptivity in the harmful UVA and UVB regions of the UV spectrum. They absorb that high-energy UV light, get electronically excited, that pop transition, but then they very rapidly dissipate that absorbed energy harmlessly as heat through vibrational relaxation or other processes, returning to the ground state, ready to absorb another photon. They act like tiny molecular umbrellas, intercepting the UV photons before they can reach our skin cells and damage DNA via those 2+2 cycle additions.
That's incredible. And thinking about color, it's not just stains or sunscreens. The vibrant colors we see around us every day, flowers, dyes, pigments, are a direct result of these highly conjugated systems absorbing specific wavelengths of visible light.
Indeed. A compound appears colored to us if it absorbs certain wavelengths of visible light more strongly than others. Our brain perceives the complementary color to the light that is absorbed. Think of the color wheel. If a compound absorbs blue light around 495 millimeter, it will appear orange to us. Beta-carotene, the pigment that gives carrots their orange hue, is a classic example. It has a very long conjugated system of 11 double bonds, which shifts its Omax well into the blue region of the visible spectrum, so we see it as orange. The key to visible color is having a highly conjugated pi system extensive enough to lower the HOMO-LUMO gap so that it corresponds to the energy of visible light photons.
So color is conjugation interacting with visible light. Amazing.
But perhaps the most astounding masterpiece of conjugation in action involving light, isomerization, and signaling is the chemistry of vision itself.
We see. How does conjugation play a role there?
Our eyes contain photoreceptor cells in the retina, rods for dim light vision, black and white, and cones for bright light and color vision. Let's focus on rods. Inside the rods, there's a light-sensitive protein complex called rhodopsin. Rhodopsin consists of a protein part called opsin covalently bonded to a chromophore, which is a molecule called 11-cis-retinol.
Retinal. Sounds like a retina.
Exactly. It's related to vitamin A. And 11-cis-retinol is a remarkably complex, highly conjugated polyunsaturated aldehyde, a long chain with alternating single and double bonds, and crucially, one specific double bond at position 11 is in the cis configuration.
Okay, so rhodopsin has this bent conjugated molecule attached. What happens when light hits it?
This is where the magic happens. When rhodopsin absorbs even a single photon of visible light, the energy is sufficient to cause an incredibly fast photosummarization of the retinal chromophore. That bent 11-cis double bond instantly flips to become a trans double bond. So 11-cis retinol becomes all trans retinol.
Light straightens out the molecule.
Precisely. This change in shape from bent cis to linear trans causes the retinol to no longer fit properly in the opsin protein binding site. This conformational change in the rhodopsin molecule triggers a cascade of downstream signaling events.
A domino effect set off by one photon flipping one bond.
An incredible domino effect. The activated rhodopsin initiates a G-protein signaling pathway, which leads to the activation of an enzyme that rapidly hydrolyzes cyclic GMP, CGMP. In the dark, CGMP keeps certain sodium ion channels open, allowing a steady flow of positive ions into the rod cell. This is called the dark current. But when light causes CGMP levels to drop, these sodium channels close.
So light stops the flow of ions.
Yes, it reduces or stops the dark current. This change in membrane potential hyperpolarization is the signal that gets transmitted through neurons to the brain, which interprets it as light.
That is absolutely astonishing. A single photon of light, by isomerizing one double bond in a conjugated system, can ultimately prevent the flow of millions or billions of sodium ions per second, generating a nerve impulse that allows us to perceive light, even in incredibly dim conditions. The sensitivity is just breathtaking.
It truly is a masterpiece of molecular engineering, all centered around the photochemistry of a conjugated pi system.
Okay, let's try and unpack all that. What a journey. We started with the basic definition of dienes, uncovering how that specific arrangement of conjugated double bonds leads to unique stability, explained by the delocalized electrons in molecular orbital theory.
Right, and how MO theory with HOMO and LUMO helps us understand not just stability, but also reactivity and interaction with light.
Then we dove into electrophilic additions, seeing how the allylic intermediate leads to 1-Ver2 and 1-4-4 products, and how temperature gives us that crucial kinetic versus thermodynamic control.
Which has real-world impact in things like making rubbers and plastics.
Absolutely. Then we entered the elegant world of pericyclic reactions, all concerted cyclic transition space. The powerful Diels-Alder for making rings.
Remembering the Cis requirement, the endo rule, and how orbital symmetry makes it loud.
Then the fascinating electrocyclic reactions, where heat versus light completely dictates the stereochemistry through conrotatory or disrotatory motion based on those Woodward-Hoffman rules.
And the sigmatropic rearrangements like Cope and Claisen, shuffling bonds around, even playing a key role in vitamin D synthesis in our skin.
And finally, we saw how UV-vis spectroscopy lets us probe these systems by looking at their Lomax, connecting conjugation length directly to light absorption. That brought us full circle to understanding how bleach works by destroying conjugation, how sunscreens protect us by absorbing UV, and ultimately how the intricate photochemistry of conjugated retinol allows us the very sense of sight.
And that really is the beauty of digging into organic chemistry like this.
Yeah.
Understanding these interactions at the molecular level, the dance of pi-electrons, the rules of orbital symmetry, the subtleties of kinetic and thermodynamic control, it genuinely unlocks a deeper appreciation for how the world around us functions, from the simplest observations to the most complex biological processes.
So what does this all mean for you listening? Well, next time you admire a vibrant flower, or maybe watch a stubborn stain vanish with bleach, or even just blink your eyes against the sunlight, maybe take a second to think about the incredible, intricate dance of electrons in those conjugated pi systems and the paracyclic reactions happening quietly behind the scenes. It makes you wonder, what other everyday phenomena are quietly governed by these elegant, fundamental chemical principles? Something to ponder. Thank you so much for being part of our deep dive family today. We really hope you feel a little more well-informed, maybe with a few more aha moments under your belt after exploring the world of conjugated systems and paracyclic reactions. Until next time.